Snell's law is an equation that determines how much light bends as a result of moving from one medium to another. Now, the bending of the light is caused because of a change in speed. And that change in speed is caused by light moving from one material that's more or less optically dense into another. So if it moves into a material that's more optically dense, it will slow down and bend towards the normal. If it moves into a material that's less optically dense, say going from glass to air, it will bend away from the normal. Now, every material has an index of refraction. So N is the index of refraction. Now we're going to have two indices of refraction in Snell's law. One for the incident medium, and that will be n sub I. One for the refractive medium, the medium we're moving into, that will be n sub r. So let's take a look at how this equation will be used. And this is the setup that I generally try and do for all of the problems. You can see in the table the refractive indices, or the indices of refraction for various different materials. So what you'll notice right away is that a vacuum and air are extremely close. Okay, so the speed of light in a vacuum would be like the speed of light in space. So that has an index of refraction of 1. And basically what that index of refraction is, it's a measure of the speed of light. So light's going to travel fastest in the vacuum, a little bit slower in air, much less slower in water, even slower in glass, etc. So let's take a look at some equations. A ray of light traveling through air is incident upon a sheet of crown glass at an angle of 30 degrees. Find the angle of refraction. Let's begin by labeling everything we know. That's going to be the boundary between our two media, and I like to sketch the normal, which is the line perpendicular to the medium change. So we know that we're starting in air. Air has a value of 1.0003. Probably could use 1 for simplicity, but we'll follow what's in the table in this first example. Crown glass. So you'll notice that there's two types of glass in the table. Almost always it's crown glass, no problems, but just make sure you notice we have crown and flint, and so refer back to the appropriate number. So crown glass has an index of 1.52. So now we're going to sketch the two. So when I move from air to glass, what would I expect it to do? Well, I would expect it to slow down. So the light is going to slow down, and when it does that, it's going to bend towards the normal. So you'll see that this angle of incidence is bigger than the angle of refraction. And I'll go ahead and label it the angle of incidence here, which is this angle. I'm going to write next to it was 30 degrees. And we're trying to figure out what the angle of refraction is. So to do that, we're going to write Snell's law, which is Ni sine theta I is Nr sine theta R. You do want to make sure your calculator is in degrees. You will not get the right answer if you are not in degrees for this. So our incident medium was air, and that has a refractive index of 1.0003 times the sine of 30. That was my angle of incidence. Theta I is angle of incidence. My refractive medium has an index of 1.52. It is crown glass times the sine of theta R. So we have some math to do. So we have to divide both sides by 1.52, so we're going to have 1.0003 times the sine of 30, which is 1/2 all over 1.52, and that's equal to theta r. So let's go ahead and type that in to our calculator. And this is a great first example because what you're going to get is that theta r is equal to excuse me. I forgot to write sine there in the equation, my apologies. So we're going to bring this up. We get sine of theta r is equal to 0.329. So that's the sine of our angle. We want to know our angle. So in order to undo sine, of course, you need to do inverse sine, which means you need to use that sine to the -1 button on your calculator. So that means that theta r is equal to sine to the -1 of 0.329. And when you type that in, you get 19.21 degrees. That is our angle of refraction. And that should make sense. We would expect that when we move from, let's go back to our sketch, air to glass, we will slow down. And we know that when we slow down, we have to bend toward the normal. And we do. And of course, if we bend towards the normal, that means that our theta r, or angle of refraction, has to be less than our angle of incidence. And that is exactly what happened in this example. Let's take a look at another. So go ahead and sketch the layout like I demonstrated above using the information in this problem. Why don't you go ahead and pause the video and do that, and then we will pick up once you have labeled it. Okay. So we have air. And we'll just sketch our angles. Notice the angle of incidence is with the normal, not with the medium boundary. And going from air to glass, so I would expect it to slow down. Slowing down means that it bends towards the normal. So this angle is theta r. So that is the angle we're looking for right in here. So we're going to use Snell's law again. Ni sine theta I is Nr sine theta r. 1.0003 times the sine of 45 equals 1.52 times the sine theta r. So we'll go ahead and do some math, and we get 0.465 is equal to the sine of theta r. So what we are going to do is solve for theta r, again using inverse sine. So in your calculator, you have to use sine to the -1 of 0.465 is equal to theta r. When we do that, we get theta r is equal to 27.7 degrees. And again, it's smaller than 45 degrees, so it bends towards the normal as we would anticipate. The next two are just additional practice problems. One, I recommend you try those. The index for water is 1.33, that's in the table above. And I think everything else you have. So 5 is one we should definitely take a look at together. So we had been calculating angle up until number 5. This time we're going to calculate index. Again, it's an application of Snell's law. It's just the angle is going to be given, and you'll be solving for n. So let's go ahead and sketch it and take a look at what we have. So we have a block that's in water. So we'll just let this be our block. Now, we are surrounded by water. So our incident medium is going to be water. And the block is some unknown index, right? And r is equal to question mark. And this is ni because it's what we're starting in. And we know that this angle is given as 31 degrees. That's theta I. And theta r, we measure experimentally to be 27 degrees. So again, let's take a look at Snell's law to solve this. Ni sine theta I, nr sine theta r. Our incident index is water, 1.33 times the sine of 31 degrees equals our refractive index, that's our variable this time, times the sine, 27. So we just need to do some math to solve this. So we're going to have to bring the sine 27 over, so we're going to do 1.33 times the sine of 31 all over sine of 27. When you type that into your calculator, just make sure you're in degrees and that you close the parenthesis in your calculator around the sine function. You do that, you should very easily get 1.5. So our refractive index in this case, or I should say the index of our refractive medium, what the light is bending into, is 1.5. A good conceptual question would be, did the light speed up or slow down when it went from water into the block? So to do that, we would simply look at the ray of light, and we would say, does it bend towards or away? So what do I mean by that? Well, if there was no medium boundary here, what would the light do? Well, it would just continue straight. And so, as compared to going straight along that orange path I just drew, did we bend towards the green dotted line called the normal? Or do we bend away from it? And the answer is we bent toward it. So because we bent toward the normal, we slowed down. So this was an example of slowing down. And slowing down and bending towards are always a pair. Now let's take a look at another example. So let's take a look at this example, number 6, sketching the normal. So we're going into a block of quartz. So this block is the quartz. And we're trying to figure out what the refractive index for the quartz is. We're incident on it, which means we'll be starting in air. And let's go ahead and sketch what's happening. So we come in at 30 degrees. Our incident angle is 30 degrees. And we bend to 20, so 20 is actually going to be closer, so we're bending towards, which again means we'll be slowing down. So right away I know that NR has to be bigger than 1.0003 because we are in fact slowing down. So let's take a look at Snell's law. Ni sine theta I is Nr sine theta R. So 1.0003 times the sine of 30 equals an unknown. In this case, we're trying to solve it. So even if it's given in the table, it's what we're looking for. Find the index. Don't write down what's in the table if it is there. Times the sine of 20. You just have to do some math. We're going to have 1.0003 times the sine of 30 all over the sine of 20. Go ahead and putting that into your calculator, making sure that you are in fact in degrees and careful with parentheses. And when we do that, we do get a refractive index of 1.46, which is the answer. So nicely done. So that is Snell's law. You can either find an index or you can find the angle. You just have to make sure your calculator's in degrees. And I think probably the most important information is the sketch that we did. The sketch forces you to identify the important information and put everything in the correct spot. It also allows you to see does it bend towards or away, and that actually helps you to check your answer. Because if you know you're bending toward, you're slowing down, so the index had to be higher. And of course, if you're bending away, you're speeding up, so the index that you're going into actually had to be a lower number. So that is Snell's law. There should be plenty of practice for you.